And yeah, his first name is a bit hard to pronounce because he's from Sweden. I do it wrongly, but it's something like Anders. So the R is ignored and it's a CH somehow, something like that. Okay, so let me just start right away. I mean, I'm in a very nice group here, and most people will know most of the stuff I will define here. But I gave this talk at another place, and there are some simple definitions here, and maybe it's also good to have the same terminology. So this is how I define a minor here. So you have graphs G and H. Actually, yeah, I learned how to use this thing. So you have graphs G and H, and then I define an H minor in the graph G to be a collection of vertices and subsets of the graph G, which are labeled by the vertices of H, right? So for every vertex in H, you have one subset of G, and these should be pairwise disjoint and non-empty and induce connected subgraphs of H. And in addition, I want that if I have two adjacent vertices in H, then these branch sets, that's how we call these sets, should be connected by at least one edge in G. So that's also what people usually would call a minor model, but in this talk I will just call it a minor. That's a slight abuse of notation. And the idea is that if you have this kind of thing, I actually have a picture on the next slide. If you have this definition, this is just the same as this conjecture deletion definition we all know. So G contains H is minor if and only if you contain such a substructure. So that's exactly the substructure that witnesses having a minor isomorphic to H. So here's a simple example. You have four disjoint sets all connected, and they have pairwise an edge in between. This is the same as K4 minor. I mean, this is actually not a minimal picture, so lots of the stuff I drew inside of the bubbles here you wouldn't need to certify K4 minor. All you need is a spanning tree, so you could like delete some stuff here and all the cycles and so on. But just a picture to show you the general definition. Right, so Hadwiger's conjecture says that if you have a graph which does not contain a complete graph on T vertices as a minor, you are properly T-1 colorable. And that's a very famous open problem graph theory that I really like and have been working on kind of a bit. And let me just quickly summarize on this slide the known partial results, which we know for this conjecture. So it's true up until t equals 6, but open for t equals 7 and all larger values. And in particular for t equals 5, this implies the four-color theorem or is equivalent to it. So that's quite a strong conjecture. And because people cannot prove the precise conjecture for values of t which are a bit larger than that, people look at the asymptotic bounds, and like the best bound for a long time was t times square root log t, so very close to linear but not quite linear. And the goal that people have been having since a while now is to push to a theta of t, so linear bound on a chromatic number. And we have come very close recently up until t times log t. So there was a breakthrough which reduced this square root log t factor to log t to 1/4 by Noreen, Postel, and Song in 2019. And since then, a sequence of papers by Postel and the last one together with Delcourt proving this state-of-the-art bound with the log t. So we're very, very close to a linear bound, but we're still not quite there. And the question is still whether you can upper bound this by c times t. Okay, so that's not what I will talk about, but just to give you some background. Let me look now for this talk at some of the small cases. What do they mean, right? So if I have no K3 minor, then I'm just a forest. I don't have any cycles, so it's triggered that I'm two colorable. And if I look at graphs excluding a K4 minor, there's an exact structure theorem for these graphs, which is not very hard to prove, which says that you have no K4 minor if and only if you are a subgraph of what is called a two tree. So in other words, you have tree widths at most 2. So you just start from, let's say, a triangle, and then you keep on picking the edge in the graph so far, adding a vertex of degree 2 adjacent to the endpoints of the edge, and you just repeat this process. And any kind of structure you can build this way is called a two tree, and these are the edge maximal graphs with no K4 minor. And then looking at this picture, it's trivial basically to color these graphs with 3 colors because you always find a vertex of degree 2 and you just remove it, color the rest of the graph inductively, and then put it back, and you have a color available for that vertex. So K4 minor free graphs are structurally constrained, and we know how they look. And for K5 minor free graphs, it's more difficult but similar. So we know that every planar graph does not have K5 as a minor because minors preserve planarity and K5 is not planar. And also vice versa basically holds. So if you have a graph which is K5 minor free, then it's structurally essentially planar. So it can be built from small pieces, each of these pieces being either a planar graph or being one copy of the special graph W8, which is called the Wagner graph, so an 8 cycle with all the opposite edges joined by these diagonals, by repeated so-called clique sum. So what is a clique sum of two graphs? You take the two graphs which you already know of that they are k5 minus 3. You take a clique in one graph and a clique of the same size in the other graph, and you just fix the matching between the vertices of the two cliques and glue them, identify these vertices along the matching, so you glue them along a clique basically, and then you get another graph. This is called the clique sum now along a triangle in this case. And this operation, if you do it either on single vertices, edges, or triangles, preserves being k5 minus 3. And everything can construct this way is k5 minus 3, and you can reach anything which is k5 minus 3 by doing these operations. And maybe sometimes when you glue something, you might delete some of the edges from the clique again. Okay. What follows from this kind of structure theorem is that if you know that you can color all planar graphs with 4 colors, because this white graph is actually 3 colorable, and these clique sums kind of preserve colorability by permuting colors along the clique separators so that they fit, you know that Hadwiger, Fatiga's wife, and the 4-color theorem are equivalent. So that's what is implied by this Wagner's theorem. So this was known since a long time, and therefore, when in the 1970s the 4-color theorem was proved, we also knew that this holds Fatiga's 5. And I'm just showing you this background to somehow like introduce a bit of the structure, which will also show up in the kind of proof ideas I will tell you, because it will be similar to this Wagner theorem. Okay, so now let me finally come to the topic of this talk. So I will talk about a strengthening of Hadwiger's conjecture, which was proposed by Holroyd in 1997. So it's a conjecture which he made and in a paper and proved for the smallest open case, basically, which strengthens Hadwiger's conjecture to something called rooted minors. And rooted minors are a concept which people have looked at a lot in the literature, and it appears in all kinds of contexts. For example, for algorithmics in relation to tree width. There's something like also in the Robertson-Seymour graph minor series this shows up. I don't know the details. So there are many things which are useful about the fact of having a KT minor, or in general an H minor, which intersects such that each branch of it intersects a given set of vertices. And that's exactly the definition of an S-rooted minor. So an H minor is called S-rooted if all its branches intersect a given set of marked vertices. So in the following, I will have the convention that always this marked set of vertices S at which I want to be rooted will usually be red vertices, and everything else will be black. So the K4 minor, this is an S-rooted K4 minor because all of these 4 sets intersect the red vertices, which basically means you can contract the branches into the 4 vertices of a K4 by going into, like, contracting into the red set in some sense. So I will actually also use a contraction definition of this notion, which is convenient to work with for some of the proofs, and you can easily see it from this picture. So basically, when we contract an edge, we somehow want to keep the colors if at least one of the endpoints was colored, right? So if you have an edge red, black, and you contract it, then it should be, the vertex should be red again. And if it's black, it stays black. And if you apply these rules, then basically you can say the graph contains an S-rooted H minor if and only if it can be contracted to an all red H using these rules. Right? So this is, I'm saying this is the same as saying the graph contains, yeah. If you basically just color red, at least one of the endpoints was red, and keep doing this, and any sequence of contractions giving an all red H is the same, is a certificate for this rooted minor and vice versa. Okay, so that's the way to think about it. Now let me just, okay. Before I can say the conjecture, which I wanted to do, let me give you the, one definition which I need to say it. And this is the one of colorful sets, and it's not very well known, so let me just say it. So if you have a graph of correct number exactly k for some number k, and you look at the set of k colorings of this graph, with respect to a fixed set as of vertices, I guess marked vertices we could say again, then we say that this is colorful if in every possible k coloring, every single color shows up on at least one vertex of S. Right? So this is a good example. So here at the top you have like a 4 clique in the graph, which obviously is colorful because you need every single color in it. So it's a 4-chromatic graph. But there's also another set, for example, this one, which is an independent set, which is also colorful because if you color with colors 1, 2, 3, and 4 here, I set up the edges in such a way that these vertices are always adjacent to everything except the vertex on top of them. So this has to be color 1, 2. This has to be color 2, 2, 3, and 4. So it's also colorful. So just to show you an example where somehow these colorful sets don't directly relate to edges inside of them, but they sometimes can be coming from the outside of it. Could actually like be forced a much longer way also, right? You could repeat this kind of process and have a colorful set somewhere at depth 1000. And actually the reason why you need many colors is like at distance 1000 from it. So it's really a global thing. That's what I want to say. Sorry, it's somehow. What I want to say is that this colorful property can be transported a long way. Mm-hmm. And another good example is like there are graphs which are studied which are called uniquely k-colorable, which is just the obvious thing you think of. So it has coordinate number k, and the partition formed by any of its k coloring is exactly the same. There's only one way to partition into k sets which are independent. And for such graphs, if you look at the unique k coloring, what the conjecture would imply is that no matter how you pick a transversal of these color classes, you will find a minor where the first branch set contains this vertex, and the second branch set contains this vertex, and the third this vertex, and so on. So it's just a special case of it, and this has been independently conjectured previously by Stiebitz, I think. There's some papers on this. But even this is unknown, this conjecture. But there's only a very special case of this for this uniquely colorable graph. Okay, so let me continue now with the... I didn't tell you the conjecture, so you cannot know what I'm talking about actually. Sorry. So here's a conjecture. It says that if you have a graph of coordinate number exactly t, and this colorful set in it, then you can find a kt minor rooted at the set. That's quite a nice conjecture because so why do we actually like think about cliques in the Hadwiger's conjecture is that cliques. So one reason you would like to think at least is that cliques are a canonical obstruction to graph coloring. They're not the only obstruction, but they are canonical in some sense. They're the simplest graph we can think of which needs t colors. And Hadwiger's conjecture says at least in some form you should find this as a substructure in your graph if you have coordinate number t. And now, if we have a colorful set somewhere in the graph, a small set in a big graph, which always needs t colors in every coloring, we somehow know that something is going on with the set which somehow, such that it's somehow rigid with respect to the coloring, and somehow having a certificate of a kt minor rooted at the set somehow tells us that, like, if this would be true at least, would tell us that really like Hadwiger, like that the relation between coloring and minors is not kind of random, but really like if you have somehow a specific part of the graph which is hard to color, you can relate the minor also to this part. So that's what this conjecture is saying, and why it's stronger than, I mean, obviously it's stronger than Hadwiger because Hadwiger is just a special case if S is a full set of vertices. Okay. So this is really, Holroyd didn't manage to do a lot here, so he proved it for t equals 3, which is quite simple. And I will prove it here. So let's see, I think it's a good illustration to see how these proofs work. So how does this work for t equals 3? And for this I will just use, yes, okay, so let me state a lemma. Or actually, okay, let me just.
So t equals 3 is like you want to find the
so yeah,
3 minor. Right?
Yeah, so you have a set, you have a graph of coordinate number exactly 3. You have a colorful set S which takes all 3 colors in every 3 coloring, and you want to find 3 sets like that which are connected and have. Right? Okay. And I'm saying like there's a very simple observation. And the simple observation says you are not suppose you have the smallest counterexample. Okay? G to this claim. Then G is not 2 connected. Like this is really a very simple case, but I will still show it. Why? Because okay, S is a colorful set which takes all 3 colors, so it has to have size at least 3. Just pick 3 distinct vertices in S. Okay, now you have 2 connected, so you have 2 different paths from S1 to S2 and S1 to S3. We have theorem. And now delete S1. You're still a connected graph, so you have some path from this path, remaining path set to this remaining path set. Take the shortest such path. It looks like that. But now you're done, right? So this is like you can easily find branches now such that one of them contains S1. One of them contains S1. I don't know, for example, like this. One of them contains S2, and one of them contains S3. Okay, my picture's not very nice, but you can imagine, right? So basically, whenever you get a structure like this where you have a cycle, and like these vertices hang like this, you can just easily define branches which you have these 3 edges. Okay, so in this case, we're just done. So it's just a very simple structure to find in some sense. And if you're not too connected, then I mean, obviously, we will do some induction, right? So let's say we have a cut vertex somewhere. X. So there's no edges from here to here. Then I look at 2 cases. First case is that either this part or this part doesn't contain a vertex from S. Okay, let's say, for example, the right part is distant from S. Everything in S lives in here. And I will just kill this part. And now by induction, I know that this graph, together with X, contains a coloring with 3 colors in which the set of vertices S, so S is a subset of this, does not have all 3 colors. Right? Because if every coloring set, most 3 colors of this set would have all 3 colors in S, then we could apply induction here. Would be small conic example. So there's a coloring of this part where, let's say, for example, let's say with colors 1, 2, 3, where no one in S has color 1. And then we also know that this part is 3 colorable, so we can just by permuting include this coloring together with the other coloring. And since every vertex was in S and no one had color 1, still no one has color 1 if we add this stuff. So it's a proper 3 coloring for the whole graph where no one in S has color 1. That's a contradiction. So that's an easy case. Now let's look at a case where both sets contain something in S. So there's some vertex here in S, some vertex here in S. And now what we do is we will also kill them, but before doing that we will ensure that we can mark the cut vertex such that it's also in S. So what we simply say is, okay, like go to 2 subgraphs. The first one is just like the left half of this vertex, so same as before, the graph is the same. But we will ensure that we will put the cut vertex into S. And we can do this as a minor operation because what we can simply say is take a path in order to generate this thing, take any path from this guy to the cut vertex and contract it. By doing so, we will make this vertex, we'll put this vertex into S. If this was a red vertex, this will be red in the end. And same. For the other one, we will just go here and contract, so this will become a red vertex. And which means now we find proper colorings of those 2 things with colors 1, 2, 3, where no red vertex has color 1 in each case. And now the point is that if we glue together, we can make sure that the permutation which we need to adjust those 2 colors to be the same is 1 invariant. It fixes 1, right? So both of them are, it's like maybe this is 2 and this is 3. Well, then just permute in the right-hand part 2 and 3, but leave 1 invariant and glue together. And then in the union, you still don't have any color 1 on S. So you might think this has to be trivial, but it's actually like these kind of things that you have to be careful when permuting to not somehow create some new colors by permuting, right? You want S to avoid 1 fixed color. And just because you avoid some color there and some color there doesn't mean it's the same. So you want to ensure that the permuting always works. So, but in this case, it's just possible, and this is the full proof for the t=3 case. And yeah, as I said, I'm just showing this because to make clear that these cuts are actually a bit more tricky than usual graph coloring proofs. Okay. Here's a statement, which is also interesting about this conjecture. So I told you that t=3 is sounds like a very trivial case, but there's some twist to this. So whenever you prove this conjecture by Holroyd for a value t, you prove Hadwiger for a value t+1. And actually you prove a stronger version of it. And I will convince you of this on the next slide. But first, here's our main result. So the main result says that this also holds for 4 conjectures. So we proved this conjecture in the first open case. So this is in some sense a strengthening of the four-color theorem, but of course in our proof we will use the four-color theorem.
Okay.
Right? Otherwise this would be kind of nice.
Does it imply four-color theorem? Oh, because of this.
Yeah, because it implies K5 minor Hadwiger. Because of the trick I will show you now. So I will actually, so I'm claiming not only does this imply the Hadwiger conjecture for t=5, actually it implies a strengthening also of this conjecture. So Holroyd's conjecture is so strong that it gives you a stronger conjecture of Hadwiger on t+1. Okay. And this has a very short proof. This is what it implies, and this is also good for larger values of t. So suppose we have proven this statement, and now I claim that the following statements are also true. So if you have any graph G which is 5 critical for coloring, so it has rank number 5 but minimal, so you're removing any vertex allows it for coloring, then I can get a K5 minor in it with the special property that I can wish for a vertex V in the graph, any vertex, and have this vertex as its own branches. This is singleton set. And this implies directly, because every graph contains a 5 vertex graph, that every graph of rank number 5 has a k5 minor where one branch is of size 1. And this is strictly stronger than Hadwiger's conjecture for 5-chromatic graphs. I have an example, I think, on the next slide. But let me just show you the proof, because this is it's very short. So look at the first statement. Take any vertex v you are wishing for and remove it. So this means that the graph G has chromatic number 5, but G minus V has chromatic number 4. Now I claim that the neighborhood of V, which is a subset of G minus V, is a colorful set in G minus V, because no matter how you four-color this graph G minus V, you should not be able to extend the coloring to V. So all the 4 colors need to show up on its neighborhood, otherwise you could have the color.
I see.
There. So it's a colorful set. So you find a rooted minor on the neighborhood with 4 branches, and then just add the singleton V to it. That's it. Okay. Now to convince you that this is very different, this is really stronger than Hadwiger's conjecture for 5-chromatic graphs, is there's many graphs. Actually, there's graphs which contain arbitrarily large clique minors and don't have a minor with a k5 minor with a singleton branch set. Okay. So take if you have any cubic graph, it's trivial, it cannot contain such a minor, right? Because you want a singleton branch somewhere, and it should have edges to all the 4 other branches, so it must have degree at least 4. So take any cubic graph, and cubic graphs can contain k 10 billion as a minor, but they still don't have a k5 minor with a singleton branch. So just to convince you that just excluding a k5 minor for singleton branches does not give you a structure theorem. These graphs can have arbitrarily large clique minors, they can be arbitrarily complex. In some sense at least. So our proof really has to talk about the coloring, not about the structure. Okay. Now let me tell you about the proof. So here's a general structure. This is divided into several parts, basically part 1 and part 2, and then we finish it using these 2 parts. And so what we, of course, look at is the smallest counterexample to the conjecture, G. So SH4 is a strong Hadwiger conjecture for equals 4, which we are looking at. So we prove, first of all, that it has a nice connectivity requirement as usual, so you prove it's a free connected graph. And usually this is the standard thing, but here, as I said, this is much trickier, and it takes up almost half of the paper to do this, because there's lots of cases and stuff. I will show you one example later. And the second problem we show, which is also important, is that the set of vertices S, so in the smallest counterexample, you have a set S which is colorful, but where you don't have a rooted K form. And such a set has to be spread out in the graph. What does it mean to be spread out? That's just something we made up. Spread out means that if you take any, so we cannot prove for connectivity, so there might be some free vertex cut. And spread out means that if you, no matter which free vertex cut you take, let's call this T, then every component after removing this cut has to contain at least one vertex of S. You cannot remove free vertices, cut into some chunks, and one of the chunks does not contain anything from S. This is impossible. And that's also because of some minimality reductions. I will show you later. Okay, so that's part 1. And now the magical part 2 comes in, which says that if you have a graph of these properties, then it's planar, and actually it's planar with a nice additional property. So take any free connected graph and a set S of size at least 4 in it. If G has no K for minor rooted at S, and the set is spread out, which is what we guarantee in the first part, then the graph GA of S is planar. What is GA of S? Add a new vertex to G and make it adjacent to all elements of S. So it's like an apex graph, but with respect to the specific set S. Okay? So in other words, you have a drawing of the graph in the plane without crossings, such that all the elements of S are in the outer face. That's the same. It's equivalent. If adding the vertex to a set makes it still planar, the same as having a drawing where all these vertices in the set belong to the same face. Okay, that's what we prove. That's a purely structural proof. The first part really uses the coloring with the minimality reductions. And once we are done with that, we know that the smallest counterexample has this property. And I will already tell you now how we finish them, so that you don't wait for the nice argument for what means nice argument, but that's how we finish now. That's the only point where we use it for color theorem. But obviously now we'll say in the smallest counterexample, GA of S is planar. Invoke the for color theorem. This gives you a coloring of this extended graph with 4 colors. Now just forget about this vertex. There's one color which does not show up in the set, right? Contradiction. That's the end of the proof. But the hard part is really getting all these properties. I mean, obviously it's not obvious why a small conic tuple has to have this property. Okay, so let's think about the two parts again. Let's first look at part one. We want to show that the small conic tuple has some free connectivity, and if we take a free separator in the graph, then every remaining component has a vertex in this. So this is really, so I've been working this out, and I was really like, this is annoyingly difficult actually. Like, maybe difficult is the wrong word, but like there's really many cases, and you cannot avoid them. You have to do them. And this proof also works here. So here I show you that if you have a cut vertex, how you can reduce to a smaller graph and apply inductions. This still works. So this way you can prove true connectivity of the graph. So let's just suppose for free now we have two connectivity already proven, right? Now we want to go to free connectivity. So we want to rule out that there are two vertex cuts anywhere in the graph. And I will give you one case that you get the flavor of the argument which we are doing. It's kind of similar to this, but I will not show you all the cases. Okay, so suppose you have a two vertex cut somewhere. So this is a separation in the graph. We always discuss this in the paper. So you have this left hand side set A, you have the set B, which only intersect in the separator, and there's no edges from A here to B here. Okay. Now we just look at this very nice case that S has at least two vertices on both sides. Okay, so we'll look at these four red marked vertices, and because we are already two connected, we have already established that, we can find two different paths from each side to the separator by Menger. And now also what you know is that there should be, if you just look at B basically, B should be connected, A should be connected, because otherwise one of these two vertices would be a cut vertex in the whole graph. Right? So, yeah, basically if there's, at the very least, there should be some path from here to here, because otherwise there's some component here hanging off this vertex and some component here hanging off this vertex, and then actually both of them would be, both of them would be cut vertices. Okay, so what I'm saying is that there should be some paths from this path to this path and from this path to this path on the left and on the right, and you take shorter such paths such that they only intersect in one vertex of each of these paths. So you get this kind of picture here. And now this is very nice because it gives us a flexibility to contract all kind of stuff onto the separator. We can either contract this path individually and this path individually and like contract here until we have only one edge left, which will give you two red vertices on the separator connected by an edge. But you can also decide to contract everything into one red vertex and make it one red vertex. And this is a flexibility we will need. Okay, so because now we need to look at these annoying cases about coloring. So case one is there exists a forecoloring of the whole graph. Oh. Yeah. Okay, yeah. There exists a forecoloring of the whole graph where the cut vertices have a distinct color. Okay? Okay, let's discuss it later. So what I can do is I can do this from both sides. That's important, right? So I can contract this edge from left and from right. I get these two graphs on vertex A and B, which have this red edge. Now, by induction, because this red set which I connect on top of this smaller graph still doesn't have a rooted K4 minor, and this doesn't have a rooted K4 minor, I get colorings of the left and the right side, which have where no red vertex gets color 1. That's always what I get by induction. So it could be like 2, 3, and 3, 4, but now the point is again, as always, I could do it like this one invariant permutation, which maps those to the same thing, and put it together. And because it's one invariant, in the total coloring, I will still not have like I will still not have color 1 on any red vertex. This would be a contradiction. And yeah, so the important part here is that why is it important that I make this assumption? You could think, where did I actually use this assumption? There is a forecoloring of the graph with cut vertices of distinct color. Because you can only call induction if the smaller graph has correct number exactly 4. But what would happen if we just do this in general is that one of these graphs has correct number more than 4. Then we don't know what to do. But because I guarantee the forecoloring with distinct colors on the cut, this induces also forecoloring on the red and on the left side, so these things actually have correct number at most 4. That's important to call induction. And then we have to look at the second case where there's no such coloring with cut vertices of the distinct color. But then there is a forecoloring with cut vertices of the same color. That's all we need. And now we do this other step where we contract everything in one red vertex on both sides. So I get these two graphs. Right? So we get a left graph I contract all this stuff into one red vertex, and thereby merge these vertices. And then for the same reason, because now there was a coloring of the whole graph where those two cut vertices have the same color, it's a coloring of the graph after identifying these two vertices. So now again, these two graphs are four-colorable. I can call induction, and I know that this has a coloring where this guy in every red vertex has no one. This has a coloring where every red vertex has no one. And I can put it together. I mean, just split the vertices again and put it together. Let's say both are 2. I can compute it. I have a one invariant permutation where both are 2, and then put it together again and have a coloring of the whole thing where no vertex in S has color 1 and a contradiction. So maybe this sounds a bit confusing, but actually, like it's in principle really simple. So only technical problem is that you need to ensure that the things you call induction to are four-colorable. If they have rectangle larger than 4, you cannot do anything with it. And therefore, you need to look at the colorability properties after identifying stuff or adding the edge. And either adding the edge or contracting always gives you still a four-colorable graph. That's the point. Okay, so that's the proof of free connectivity in one of the cases. Then you have to look at the other cases where S is distributed differently, but they work sort of similarly. Now let me show the proof of, which is also morally similar, of the spread out property. So let's suppose we know now that we are free connected, and towards a contradiction, suppose there would be a set of free vertices which splits the graph into several components. So there's again like a separation between some set A and some set B, and suppose that like there's one component, let's say the set B, which doesn't contain any vertex from S. So S is contained on the left side. And now there's some case analysis here again. I told you like the whole proof is like there's lots of cases, and I'm not sure. I'm showing you only a fraction of it. So first case is that B on the right hand side has only one vertex, which seems like a stupid case, but actually it's kind of relevant because there's one important argument there which otherwise doesn't work. What if there's only one vertex? Why doesn't this make sense? Right? Because then it's a vertex of degree 3 at most. So just kill this vertex, call induction here. You get a coloring here where no vertex in S has color 1. Put a vertex back in color it just greedily, and because this vertex is not in S, we don't care about it. It can have color 1. We are happy. Okay. So we know that B without A has size at least 2. And that's actually important for the next argument, because now we call this statement by Holroyd and also by Lemmas and Wood, which is basically just an extension of the argument I showed you here. I told you here that if a graph is 2 connected, for any free vertices I can find a root minor. But actually there's a weaker condition which still guarantees it. And this is an exact characterization. So if you have a graph, and now you have 3 given vertices, 3 marked vertices, and you want to find a k-free minor rooted in it, then this exists if and only if, or this does not exist if and only if I can kill one vertex in the graph and thereby separate each of A, B, C in its own component. Yes?
VB equal to 1 of A, B, or C.
Yes, that's important.
Just
that's one of the options.
Like you said, there are distinct components.
No, but I mean, it's like you just don't consider vertices which don't exist anymore. Basically.
Yeah.
Okay, yeah, maybe that's fine if you just contact. Yeah, but that's a good point. V can be one of A, B, and C. And if you want to see like why is this true, it's also not. I mean, that's also very easy to prove. So we know it's true if the graph is 2 connected, and if the graph is not 2 connected, you can just look at the block decomposition basically, and ask where these vertices sit. And basically, if they are all in the same block, you're done. You again find like you do the 2 connected argument. And if 2 of them are in the same block, and the other one is somewhere else, say A and B are here and C is here, you can just like find a path from C until it reaches the block and project C into the block, and do the same argument from there. Right? You just contract this path, make that like get a C prime here, which is then also red, and then make the argument here because the block is 2 connected. And finally, if they are all in different blocks, again, this would still be a good case because then you can somehow look at the path, let's say from A to C and from B to C, and you see whether these cut vertices stay. So there's like one center block, right? Let's say C is in the center. You look whether they enter through different points. As long as they enter through different points, you can again project. You get a B prime here, an A prime here, and these are 3 distinct vertices in a 2 connected graph. You can again find the root minor. And the only case in which this doesn't work is like you have the center block, and 2 things project basically along the same cut vertex there. Because then you don't get a different projection. But then this middle vertex, if you kill it, separates all of A, B, and C. That's why this is true. Okay, so we need, so why do we need this now? Because we want to find a rooted K3 minor in our case, and we want to understand why it's possible. So remember the statement says, so what we want to find now is on the right hand side in B, a rooted K3 minor at these three vertices, or the catch vertices. I claim it exists. And the reason is that I claim, just looking at the graph G induced on B, I cannot separate these three distinct components by just killing one vertex. Okay, so the reason for that is, suppose you kill some vertex, let's say for example this one. There's at least one other vertex in B without A. Look at this vertex, and recall that the whole graph is free connected. So by manga I get three different paths from this vertex to the separator. And at most one of them can get by this additional vertex, so two of them remain, but then this is a witness that these two vertices in the cut are in the same component. So no matter which vertex you kill, two of them are in the same component. So these three vertices have the property we want, and so we get a rooted K3. Yeah. So we get three branches, each containing these things individually, and the pairwise connected in B. Okay. Why is this nice? So because this again gives us the flexibility to basically contract anything on top of the separator we want. We can either contract each of the sets individually, and we get a triangle here. We can, for example, contract those two sets together into one thing, thereby merge those two vertices, and we have an edge between the merged vertices here and the bottom vertex, or contract everything into one. And again, this will resemble all the possible color patterns that can occur. That's how the proof goes. Right? So we say, look at the forecoloring of the whole thing, and look, take some forecoloring of the whole graph, look how it looks. If they all have distinct color, then just do the normal contraction where you contract a triangle on top of it. Then this graph is still forecolorable. You can call induction, and because there was nothing in S, we don't need to be worried about that. So there's no, we get some forecoloring where everyone in S does not get color 1, and we can just put the rest of the coloring of the whole graph on B and merge it with it. And then the second case is, what if there's a color pattern like this? It looks like the same, but this has a different color. Well, then contract the top two ones in one, and the bottom in its own one, and then like again, if you get a coloring here on the left side, it has exactly this color pattern, and you can expand it. And by permuting, this was a bit quick, you will get the same thing. That's really the whole proof, and if they're all the same, then you contract everything into one. So this is the proof of the spread out property. Okay? Yeah, this is a very funny picture which I found on the Oberwolfer homepage. So I was looking for pictures of Hugo Hadwiger for a talk, and then I found this very funny picture. I don't know, like, whatever. I just found some people might find it funny. I was surprised myself by seeing it, but I forgot about it. Okay, that's fine. Okay, so what we proved up until now, subject to lying about some things, is that we are free connected and the set S has a spread out property. And now we want to use this in the second part to show that GA of S is plane. So we want to prove this lemma. And what the essential truth for this lemma will be a structural characterization of when you have, in which situation. So let's say we look at this rooted K4 minus from a structural point of view, and we want to understand how do the graphs look which don't have, at a given set of 4 vertices only, of size exactly 4, no rooted K4 minus. And this question has been looked at by Fabila Monroy, I guess, and Wood, and they characterize exactly the edge maximal graphs not having this structure. So you have 4 marked vertices, and what are the edge maximal graphs which don't have an ABCD rooted K4 minor? And they gave a precise list of like 8 different classes of graphs, I'm not lying, which don't have this, and they are the only ones. So every other graph which doesn't have this property is a spanning subgraph of one of these classes. And we decided in our paper to not go through all these cases because there's some essential properties in many of the cases which we can use for our proof, and we don't need the exact structure theorem. So there's a weaker statement which directly follows from the characterization, which is this one, and this is good enough for our proof. So if you don't have an ABCD rooted K4 minor, then your graph is either a spanning subgraph of something which they call an ABCD web, and I will have a picture on the next slide. This is a very nice case. And otherwise, you have a pair of vertices in the graph such that deleting them does not only disconnect the graph, but actually you get 3 different components by deleting them. That's just how the structure theorem looks. I mean, you just go through all the cases, you look at the first case is basically a web case, and all the other cases just you find these 2 ways. You have to believe me. Okay. Now this is an ABCD web. Not quite, but almost. So let's first define this basic structure. So you have A, B, C, and D on the outer face in some permuted order, as you can see. Doesn't matter which permutation. It's an inner triangulation, so they form a 4 cycle. And then you have an inner inner planar triangulation of this thing. So just a planar graph where all the inner faces are triangles and the outer face is a foregon. And it's also internally four-connected in the sense that you don't have separating triangles. So every triangle you see in the graph really is a face and not something bigger. Okay? This is the basic structure for an ABCD web, and then on top of that you can take any facial triangle of this picture and glue something on top of it. That's similar to, that's why I told you this is similar to the Wagner structure theorem, where you can do these click sums. So now that's what they say. So they say an ABCD web is a graph which is a spanning subgraph of such a structure, meaning this kind of triangulation, and then anything attached on top of triangles. This can be any graph. And the whole point is that it doesn't matter how these graphs look, because they are attached at only 3 vertices. If you look like this, you will not be able to find an ABCD rooted K4 minor. That's easy. So there's one thing like, is this a planar graph? So things, basically if you want to connect C to D and A to B, they have to cross and you can't cross. That's one problem. And the other problem is that you cannot really make use of these additional things, because all you can do is you walk inside of them and outside of them, like you take like a detour inside of them, but then why didn't you take the direct edge of the triangle? That's basically the reason why it's not helpful to use these things. Okay. So that's the one canonical obstruction to having the rooted minor. And the other one is having these two vertices, such that deleting them splits you into at least 3 components. Believe me. Okay. So here's the idea of our proof. Because what we in the end want to show is that adding one universal vertex to everything which is red, right, to everything that's at S is planar. But how do we do this if we only know stuff about 4 vertices? And there's this very neat trick which is actually quite simple to prove once you realize it, that all you need to do is, you need to do this for any set of 4 vertices in S. And then you're done. So the claim of this lemma is that if you take any 4 subset, A, B, C, D in S, and you can find a planar embedding of G where only those 4 vertices are on the outer face. But for every subset, then you can also find an embedding of a planar graph where everything is on the outer face. Okay, and you think like this, it looks like why would this be true? But like there's a very simple proof. And if you think for like 5 minutes, you will find it. But we don't have this time, so I will tell you a nice proof. Okay, it's by contradiction. And it uses a thing you all know, it's Kuratowski's theorem. Suppose this graph GA of S, suppose this is true for every 4 subset of S. Suppose GA of S is not a planar graph. What does this mean? It means that it contains a minimal non-planar graph, edge minimal non-planar graph. What are edge minimal non-planar graphs? They are either a subdivision of K through 3 or a subdivision of K5. So these are both of them are of maximum degree at most 4. Right? So we have this graph, we said it's non-planar. It contains an edge minimal non-planar subgraph of maximum degree 4, which still is non-planar. But then look at this vertex. Out of the edges of this vertex, at most 4 can be used. So then just, if this graph is not planar, then of course the graph where you just attach this vertex to the corresponding 4 edges, vertices which have been used, was also not planar. But this cannot be, because we have a planar embedding where those 4 vertices were on the outer face. So we can connect the vertex to it and make it thinner. Right? So if you have a certificate for non-planarity, it's bounded in degree, which means you will not need all the connections to S to certify it. 4 of them will suffice. Okay? So now this comes in very handy, because now we can, in fact, look at only 4 vertices. So the goal will be now we are given any subset A, B, C, D of 4 vertices in S, and we want to find the planar embedding of the graph G, where those 4 are in some permutation on the outer face. That's what we will prove now. Okay, and what we do is we just say, okay, this is a subset of S, so we will not have an ABCD rooted K4 minor. Right? Otherwise we're immediately done. So we can apply the Monroy structure theorem, and there's 2 cases of it, and I will do basically both cases. So let's first look at actually, no, sorry, this comes later. So let's go back quickly to the structure theorem. So the first case is this web case, and in the second case we have a separator of order 2. But we are in this lemma which we are now proving, we already have 3 connectivity guarantees. So we cannot go in the second case when we call this theorem. So really, what has to happen is the first case, that we are a spanning subgraph of an ABCD web. Right, so we look like this, and actually just to make you aware, like, we are just a spanning subgraph, so we can be missing any number of edges. So for example, like this doesn't have to be a triangle and so on, right? Okay. So now we want to. So we already have this nice embedding of this thing where A, B, C, and D are on the outer face. But of course we have these big question marks, like these attachments here. We don't know what happens with them. if there would be no red vertices in these attachments, we would have no control whatsoever about them. Because all we have is information about red vertices, that there's no rooted minor red vertices. But we have the spread out property. Don't forget that we have the spread out property, which means that for every free separation in a graph, all the components have a red vertex. And this is crucial now, because this will allow us to also deduce structure on the attachments. So if you take away this triangle as a separator, so there should be something red in here, something red in here, something red in here, and so on. That's why it's crucial, because without the red vertices we have no structure, but when they are there we have a lot of structure. And they are everywhere. That's what it's spread out. Okay? So now, so all we need to do is now, the idea will be to simply embed these planar attachments into the faces. So to find it, so look at the graph for each attachment, look at the graph consisting of these three vertices plus the rest. Find an embedding of these graphs where those three vertices are on the outer face. And then just permute it correctly and glue it into this embedding. And this will be planar overall, where A, B, C, and D are on the outer face. When we manage to do this for every attachment, we are done. So all we need to prove is that we can always do this for every free separator in our graph, which has like A, B, C, and D on the one side, and then something else on the other side. We can find a planar embedding of the right-hand side of the separator plus the separator vertices, where the separator vertices are on the outer face. And that's exactly the last lemma which we have to prove. It says exactly this. We have a frequent graph spread out. It's the same assumptions as in the other statement. And now you have a separation AB, where A is the left side, B is the right side. And on the left side you have at least three vertices. Okay, we obviously have this, because we actually have at least four vertices on one side. Then you get a planar embedding of the right hand side, where the separator is on the outer face. And the reason you might wonder, like, why do we assume only three vertices in A and not four? Because we could assume four in this application. But the reason is that we will prove this lemma now by induction. And for the inductive, to make induction work, you need to assume less. Okay, so let's prove this statement. And this will be like the.
Yeah, you can move the board.
Yeah. So this will be an interesting proof. Okay, so we will actually again use this Pavilla-Monroy structure theorem. That's why I got confused earlier. Okay, so we prove it by induction on the side of the right-hand side of the separator. Okay, so the base case, if there's exactly one more vertex on the right-hand side, so if B is of size 4, right? But in this case, the statement is trivial, because we have a graph on 4 vertices. There's a subgraph of K4, and you can always embed such a 3 given vertices on the outer face. It's trivial. Okay, so we can assume that mu about A is at least 2. Also, some simple observation here, because we are free connected, actually both, so let's just note some statements here which are true. Both G induced on A and G induced on B are connected. So it's just like, if one of these parts is disconnected, the separator would contain a smaller separator, right? It's like this has several components, then there would be a 2 separator somewhere. And there's a sequence of claims here, and I keep forgetting it. That's the only reason why I brought this paper here. Right. Okay. Right. So now what we claim is that there exists a way of labeling the vertices. Okay. Basically, all we claim is the following. So you can find like okay. So the assumption is that S has at least 3 vertices. A has at least 3 vertices in S. So let's say we take some vertices here in S. By the way, A also includes a separator, so they could already be on the separator. So when I talk about paths, and the following paths can always be of length 0. Okay, so these are, wait, maybe actually let me use the color again, because these are like the important vertices. What I can do now is I can apply Menger's theorem towards the separator, so I find 3 vertex disjoint paths like this. And the separator vertex I call C1, C2, C3. And then there's an additional claim here, which is this is the thing about claim 3, which says that actually I can, so this is always possible, but actually I can do better. I can find, I mean this is quite trivial to see, so I will not make a full argument for this. You can extend these paths to connected sets of vertices, such that you will have an edge between this set of vertices and this set of vertices, and this set of vertices and this set of vertices. maybe not between the top and the bottom, but between like this and like this. Okay, actually, why not? Let me make the argument. It's simple. Okay, so let's say I have like these three vertices here, and now among all such, okay, basically you just pick an ordering of these vertices here, such that the minimal distance in the graph, g of a, between S1 and S2, plus the minimal distance between S2 and S3 is minimized. I mean, there's many ways of doing it. You could also just like first say, this is one way, and then you can see that like,
do you allow permuting these S3?
Yeah, exactly. You're allowed permuting them, and that's why it's trivial, because you can just take a path between the shortest path between any two of them, and then take a path from the third one to either of them, and then whichever it hits first, you take. That's basically okay. It's really simple, but like just like let's fix a labeling of the separator and of the vertices such that you have like basically a connected set here, connected set here, and connected set here, such that they are adjacent like this and like this. That's the claim proof. That's easy. Okay. Right. Now another easy observation is that I can actually. Okay. Let's look at. The set B, and suppose we kill at most two vertices from B. Okay? So let's say we have a set X in B of size at most 2. Then in G of B minus X, every component contains at least one vertex from the separator. Okay? And this is also easy to see because just like pick some vertex here, find three disjoint paths. Okay, sorry. So if X is a full set here, then so X has to contain something from the. Okay, if these are two vertices only and X is everything, then you're done because then the only components are those three vertices. So X misses at least one vertex here. So pick that vertex, take three disjoint paths there, and X can hit only two of them. So this is in the same component as something in the separator. And this holds for every vertex outside of X here. Every vertex outside of X here has three disjoint paths there. X can kill at most two of them. So it's in the same component as one of the guys in the separator. And obviously they have this property too. So everything, the claim is that if you kill two vertices, then every component intersects somehow this separator. Okay. Okay. Yes. So now we look at another case. So now let's say so the next thing I will claim is that the graph induced by B. Okay, let me actually write. So 3 was the thing with the paths. 4 was that every component after removing most two vertices intersects the separator. And now the next thing will be that G of B is actually two connected. Or mod, okay. It's either two connected or we are done. Okay, so yeah, let's see why we are done if G of B is not two connected. So let's suppose now the case G of B has a cut vertex. And call it, let's say, X. Right, so we have again the same picture. And there's some vertex here, such that killing this vertex destroys connectivity. Right, so all the remaining components contain C1, C2, or C3, and so there's one component which contains at most one vertex from these. Right, so for example, there's a component which contains only C1 and nothing else. Okay. Now, the claim is that this component contains only C1. Okay, why does it contain only C1? Because suppose there's anything else in there, this is not empty here, then you could separate this anything else which is in here from the rest of the graph by killing only C1 and X. But we said if we kill two vertices, every component contains something separated, but this wouldn't. So this has to be trivial, this is only C1. So if you remove X, then one of the vertices in the separator is in its own component, but this also means that this one vertex does not have any neighbors anywhere else. So the only neighbor of this guy has to be X. Only adjacent to X, or yeah. Otherwise we're not free connected. Okay, but this is actually nice because now we can do induction. So the setting here is that we have some vertex here, such that this is the unique neighbor of C1 there. So then obviously you can also take, instead of taking the separator C1, C2, C3, there's this there's a small separator, namely X, C2, C3, right? If you just take these three vertices, then still it's a separator because C1 can only reach over X. And it's a separator which has a smaller right-hand side. It's by one smaller than previously. So now, you know why we do induction on the size of B, because now we can call induction. Which tells us that this graph, G of B minus C1, can be planarly embedded where C2, C3, and X are on the outer face. Right? Well, but then just embed C1 also and connect it to X because that's its own neighbor and it's still on the outer face. That's it. So that's why G of B cannot have a cut vertex, because then the vector has to look like this, and then you can easily done by induction. So we can suppose, that G of B is two connected. So now we will finally, soon we will reach a nice point here in this proof. I'm sorry, okay. Yes. So now we have that G of B is two connected and B has size at least 5, right? And now what we will do is we will basically use the fact, so this is very important, that we have these three vertices here and we can project them by these paths onto the separator. So what we will try to do is find a rooted minor so we try to find a C1. Okay, okay, so what a spread out property implies is that if we kill the separator, B has to also contain a red vertex. And we call it S4. And now the idea will be that we use these paths here to project S1 and S2 and S3 onto the separator, and then try to find in the smaller graph in G B a K4 minor rooted at C1, C2, and C3 and S4. And then we can extend, if we find this, we can extend it using these paths so that it actually intersects 4 red vertices as we want. Okay, so we know that, so we try to find a C1, C2, C3, S4 rooted minor in G of B. And it doesn't work. We know it doesn't work, otherwise we're done. So now we can call the Fabila-Monroy theorem once again. So we get either this structure, or we get, now it can happen, because now we are only two connected and a free connected, now it can happen that also this other case occurs with two vertices which give free components. So we have case A and case B. So case A says that G of B is a spanning subgraph of a C1, C2, C3, S4 web. Right? So exactly the same picture, only that C1, C2, and C3 are on the outside, and S4 is also there. And in the end, what we want to find is just an embedding. So this is quite nice because we want to find an embedding where the separator, so C1 and C2 and C3, are on the outer face. So it's the same game again. So again, everything is already planar, and the only thing we need to do is also embed the attachments. But now again, it's nice that we can call induction, because these attachments again will give you free separators in the whole graph. Again, you will know that they contain red vertices, but now you will just know by induction that these attachments have the embedding. And then the whole thing has the embedding. And C1 and C2 and C3 are on the outer face, and you're done. That's why case A is actually easy. Just induction. Case B is a nasty case. So let me give you the picture here. So here's the separator, right? So these are separator vertices. And now we have two other vertices, u and v, such that killing them creates three components, at least three components. But actually, we know that they have to create exactly three components, because remember the claim that if we have a set x of size 2 and we kill it from v, then every component contains one vertex from the separator. But we want that there's at most three components, so at least three components, and then also at most three components. So it has to really look like this. After killing it, there's one component C1 containing C1, there's one component C2 containing C2, and one component C3 containing C3. That's the only way. Otherwise, we have less than three components. And then there's also U and V somewhere, which we killed. Okay, so this is that's how B looks. We always only talk about the graph G of B, no? And S4 is somewhere in the picture. S4 is somewhere here. It's not one of those three, somewhere there. Okay. Now we look at where could S4 land. Okay, and then we will just always construct this rooted minor now. And also, actually now it will be important that we have these paths on the other side. So like this is all B here. For A, don't forget that we have these connected sets which have the property that there's these edges here. Okay. So basically, we look at where is S4. And in order to do this in a sensible way, what we first do is we again call Menger's theorem, and we say that from U, I have from U I have three disjoint paths to the separator. From V I have three disjoint paths to the separator. That's a bit of an ugly picture. But the idea of it is that, okay, so S4 lands either in one of these path sets or in one of the components here, or somewhere outside in one of the components. If it lands somewhere outside of the components, we can just again take the shortest path to one of these paths and somehow map it into this path set. The union. So path set. By path set, I mean the union of the vertex set of the paths. So in this case, if S4 lands outside, we just take the shortest path to the union of these three paths or the union of these three paths, where we always exclude the endpoints. So let's say we get this path. And in this case, this is just the same, will be the same as a case where S4 just is on one of these paths. We can just project it sort of again on these paths. Okay, so just suppose that S4 is contained in one of these paths. Otherwise, take the shortest path towards one of these paths and pretend it would be there. Look at the S4 prime. Okay, now we are really almost done, because S4 is either in a, so there's like these forks, right? I mean, there's like either this structure which comes from U, or this structure which comes from V. And these are connected sets, which each of these is a connected set which attaches to each of C1, 2, and C3. It has at the end an edge to C1, at the end an edge to C2, and an edge to C3. Right? So what our idea will be to take these three branches here, and then one of those. And this will always work because S4 is either here or here. And if S4 is, let's say, here, then we just take this branch that it contains S4. Right, wait. Yes. It connects to all those three, and we have those two connections, and only one of them is missing. Right, so, okay, what is the structure? If we want, so let's say we have this case, what we get is like one set here contains S4, has edges to all of these three sets, and we have these connections. So all that would be missing is an edge from here to here, right? But we can get it by not forgetting the fact that we also have these other disjoint paths. Or there's another way of saying it. You could also say, if I wait, should I confuse myself here? Actually, I might have gotten this slightly wrong. This is like Oh. Yes. Okay. I think I finally have it. Yeah, okay. So everything is correct except that I defined the paths wrongly. So as you see, what I wanted to say is that I can use this to connect up like the 1 and 3 set, right? But obviously, like this must not be disjoint from the other 3 paths, because I just said take 3 disjoint paths here, take 3 disjoint paths, but they could overlap. That's why you don't do it this way. So you don't do 3, 3, but you do 2, 2, 2. So you take 2 disjoint paths between C1 and UV, 2 disjoint paths between C2 and UV, and 2 disjoint paths between C3 and UV. You again get this collection. You can do this, define the same sets, but now you know that from each vertex here, if you take a different vertex here, the paths going there will be disjoint. And then, if you want to connect those 2 sets, you can really just go via the path from C1 to D, let's say, and then back to C3, and thereby connect those 2 sets without touching S4. I think that's it. And if I got confused, then I'm sorry, but I think we can maybe... Okay, whatever. I think it makes no sense to get back on it. But I think it's great. Well, so this embeds this proves this lemma, which embeds the whole planar graph with 3 vertices on the outer face. We can use this to get the stuff into the faces in the original proof, and get for every subset of size 4 of S an embedding where those 4 vertices are on the outer face. This proves that GA of S is planar, and then we call the four-color theorem. So that's the proof. Yeah, so let's have some outlook here. My talk is finally finished. So Holroyd's conjecture for 5-chromatic graphs would be very interesting, but it's also very hard, because it would improve Hadwiger's conjecture for 6-chromatic graphs, which has a very, very long and complicated proof by Robertson, Seymour, and Thomas. Also, what falls out of our result is that the K5 minor, so every 5-chromatic graph has a K5 minor with a singleton branch. And then we wondered about, like, in general, this question: how many branches can we make singletons in a K5 minor? And you obviously cannot make more than 2 singletons, because you don't have triangles necessarily in a graph of high-chromatic number, but maybe 2. And we can. So I kind of believe it's true, and I kind of convinced Anders. And there's a very short proof that it's true for t equals 4. Let me show it, because this is a really neat proof. I actually haven't seen this anywhere. I'm sure it's kind of known, but for some reason I couldn't find it. And this is maybe even the shortest proof I know of the fact that a 4-chromatic graph can always contain a K4 minor. So here it is. Okay, so we want to prove that a 4-chromatic graph contains a K4 minor. Actually, let's prove the following statement. If the graph has chromatic number 4, then it always contains a K4 subdivision where one of the paths is just an edge. This is always true. Has anyone seen this statement? Because I haven't. And it has a very simple short proof. Here's my proof. Take the smallest, so take any 4-chromatic graph, take a subgraph of it which is 4 edge critical. Mm-hmm. And I only need 2 properties from this. Property 1 is that, so let's suppose the graph is critical. Property 1, which a critical graph has, is that the minimum degree is at least 3, because if you have a degree 2 vertex, you can remove it, color the rest, and add back the color. The second property is has no clique cut set. This is a general property of critical graphs. If you have a clique, which is a cut set, for example, an edge in this case we just care about edges actually, then yeah, you can just color the left-hand side, the right-hand side, and then permute and fit together. Okay, and these properties already imply having this structure I'm saying. And here's a nice proof for it. Take the longest path in the graph. Look at its endpoint. It has at least 3 edges. One of them is this one here, but there's at least 2 more, and they have to go back, otherwise the path is longer. Okay, what did we find by doing this? We found an edge which is on 2 disjoint cycles. Right, so do you see which kind of edge I mean? It looks like this, it's an edge. And there's a path here and a path here. They don't share vertices. But that's it. Because this edge is not a clique cut set. So there's a path.
Okay.
Have you ever seen a shorter proof for like the fact that 4-chromatic graphs contain K4 subdivision? And it proves a stronger statement. I've never seen this, it's very strange. Okay, whatever. Yeah, that's it. So that's true for t equals 4. For t equals 5, we don't know. We just get one singleton. We don't get two. Yeah. Okay. Thank you. And now I will.
Thank you. Questions?
Is there some asymptotic measure for Stern Hadwiger conjecture? So
Asymptotic version? Yeah, I mean you could
for
also
example-
try to. Oh wait.
But for example, finding kt over log t minor, something like that.
Yeah, I guess you could just say, suppose we have a colorful set. We want to find a smaller minor root of it. I think that's what you could do. But yeah, I'm not sure. Interesting, but yeah, there's a version. Maybe there's another version also. I mean, you could just look at the largest minor you can root at a given colorful set. That's what you mean.
So I guess the thing with the singleton branch sets
Yes.
makes it look a little bit more like
A subdivision.
Like a subdivision.
That's
right?
true. For a subdivision, you would have one, but this is not known. It's a big open problem.
Wait. that's-
There is a open question, which is still not answered, and it's a big, well-known question, whether a 5-chromatic graph has a K5 subdivision.
So that's isn't it?
And this is a stronger statement than our statement. Okay.
Yeah, there's a one open case for Hegel's conjecture, right?
Yeah,
That's
this is the open case. Yeah.
But I guess you could try and have some conjecture which says, well, just a question of like, what's the threshold between Hegel's conjecture and Hadwiger's conjecture that you?
Yeah,
can
yeah.
actually-
How many edges don't you need to?
So, but so,
Yeah,
so
no,
you
more
could
like-
so this is like
Yeah.
how many?
Yeah, I was
Of
thinking.
your- yeah.
I was thinking about how many branches can you make a single film, but you can also think about like. No, actually, I'm not sure. What is the other version you're thinking of?
Well, yeah, I guess
That's so obvious.
you want sort of some minimal minor which
Maybe you want to minimize the number of split vertices or something. Or
you sort of allow to
like-
take a yeah.
I don't know. Like there's many versions you could many ways you could measure this, but this is exactly the direction this is going into.
Yeah.
It's just very hard, I think, these questions. Yeah. And also, like this kind of statement is still weaker because the statement we are proving is really showing that for a critical graph you can take any vertex. And this is stronger. Right. So it's not comparable to the other conjecture.
Yeah.
Just a corollary. Yeah.
Let's see, since we spend a lot more time than usual, let's thank the speaker.